My name is Elizabeth Slate. I'm professor in the Department of Statistics at Florida State University. This is the inaugural Hollander Distinguished Lecture, an annual lectureship that recognizes an internationally renowned leader and pioneering researcher in statistics who has made a sustained impact on the field. I thank all the departmental, college, and university personnel who made this event possible in this unusual year. I also thank our sponsoring societies, the American Statistical Association, the Institute for Mathematical Statistics, the National Institute for Statistical Sciences, and the Statistical and Applied Mathematical Sciences Institute. To initiate our proceedings, please welcome Dr. Sam Huckaba, Dean of the College of Arts and Sciences at Florida State University. Sam.
Thank you so much, Elizabeth. Welcome, everyone. It is a great privilege to join you and to make a few remarks. I wish, of course, we could be hosting you in person at our beautiful campus and in our city, but that's just going to have to wait, perhaps next year. I know that this event has drawn an audience that spans the globe. Welcome to all of you, wherever you are. We are very fortunate to have with us a distinguished statistician, Dr. Nancy Reid from the University of Toronto, to deliver today's lecture. Welcome, Dr. Reid, and momentarily there will be a proper introduction of Dr. Reid. I also want to recognize our campus leadership, President John Thrasher, Provost Sally McCrory, who are both attending. Welcome and thank you for attending. I know that you have a busy schedule, especially now. Myles Hollander, I want to say a few words about him before I pass this onward. Myles got out of the gate quickly, as we say. He earned his doctorate from Stanford when he was 24 years old and hit the ground running. Some would say sprinting. The very next year, he and his wife Glee moved to Tallahassee, where Myles launched what would be a flourishing academic career. As his research and scholarship thrived, Myles helped build FSU statistics into a top department. This included serving as department chair on 2 different occasions, and also at crucial times, I might add, along with supervising and co-supervising 19 doctoral students. Myles helped set the stage for spectacular growth over the last decade. Since 2010, the faculty size has increased by 75% in statistics. The number of graduate students has increased by 181%, and the number of undergraduate majors has more than tripled, increased by 236%. This growth shows not only the important place of statistics as a profession and an academic discipline, but it also reflects the great departmental leadership that we've had over the years. As you will read, Myles Hollander has deservedly received many honors and awards over his career. I want to mention just one of these, an internal award. In 1998, Myles was chosen to be a Robert O. Lawton Distinguished Professor. This is the highest faculty honor at Florida State and is awarded to at most 1 faculty member each year. You just simply don't get that award unless you've done it all, which Myles has. And in addition to this, to all of this, Myles is a nice guy. And he's also a great dinner companion. Myles, Marlena and I look forward to going out with you to dinner as soon as we get past this pandemic. This concludes my set of remarks, and Myles, I will now turn the microphone over to you to say a few words. Thank you so much for your attention, and I hope you enjoy the lecture.
Thank you, Sam. Welcome, everyone. I endowed this lecture in appreciation of Florida State University, its statistics department, and the statistics profession. Statistics is an exciting field. statisticians get to work on interesting, challenging problems and get to advance science. My major professor, Lincoln Moses, would get up very early every morning, sit down at his desk with a pencil, a couple of pencils, a pad of paper, a cup of coffee, and say to himself, let's make science. In my graduate studies at Stanford, and in my career at Florida State, I benefited from meeting, listening to, and learning from great statisticians. They were inspiring. This lecture series will help our students and others to have similar opportunities. In 1992, Nancy Reid received the COPS Award. The acronym stands for Committee of Presidents of Statistical Societies. Only one such award is given each year. The recognition was based on Nancy's work to that point and her promise for the future. Nancy has far exceeded that promise. She is one of the world's most influential, honored, and revered statisticians. Nancy, on behalf of the university, the statistics department, and personally, I thank you for being the inaugural lecturer. You set the bar incredibly high for future speakers. Now I turn this presentation over to my colleague, statistics professor Elizabeth Slate. Thank you, Elizabeth, for all you did to bring this lecture to fruition.
Thank you, Myles. It's now my great pleasure to introduce the inaugural Hollander Distinguished Lecture, Dr. Nancy Reid. Dr. Reid is University Professor of Statistical Science and Canada Research Chair in Statistical Methodology at the University of Toronto. She obtained her PhD from Stanford University in 1979 and taught at the University of British Columbia before moving to the University of Toronto in 1986. Dr. Reid is renowned for her influential research advancing theoretical statistics. A major focus of her work is elucidating general principles for using information from noisy data as efficiently as possible. She pioneered methods for refining the likelihood function in its many forms to sharpen resulting inferences. Her insights have shaped both the foundations of statistical inference, including the interface between frequentist and Bayesian methods, and applications to complex data. This has led to influential contributions to diverse fields outside statistics, including biology, environmental sciences, surveys and public policy, and high energy physics. Dr. Reid has provided leadership throughout the profession. She has chaired the Department of Statistical Sciences at Toronto. She has served as the president of the Institute of Mathematical Statistics, as president of the Statistical Society of Canada, as vice president of the International Statistics Institute, as scientific director of the Canadian Statistical Sciences Institute, as editor of the Canadian Journal of Statistics, and as author of several influential texts. Among Dr. Reid's many professional honors are the prestigious COPS Award that Myles mentioned, the President's Award of the Committee of Presidents of Statistical Societies, and from the same group, the Florence Nightingale David Award. She is Fellow of the American Statistical Association, Fellow of the Royal Society of London, Fellow of the Royal Society of Canada, Fellow of the Royal Society of Edinburgh. She is Foreign Associate of the U.S. National Academy of Sciences. She won the Emanuel and Carol Parson Prize for Statistical Innovation and the Gold Medal of the Statistical Society of Canada. In 2014, she was appointed to the Order of Canada for her extraordinary contributions to the Canadian nation. I hope this provides a sense of the magnitude, depth, and diversity of Dr. Reid's contributions. Of course, I've only skimmed the surface in order to preserve time for her presentation. During her talk, please enter all questions into the Zoom chat window, and these will be addressed in turn following the presentation. Dr. Reid, we welcome your talk entitled 3 R's: reliability, replicability, reproducibility, the interplay between statistical science and data science.
Thank you very much. I'm a little bit overwhelmed by all these nice things being said. It's very kind, Myles. It's especially nice to hear from you, and to, of course, to be the inaugural Myles Hollander Lecture. Myles and I go back a while. I first met him, I think, in 1979, and this is a picture that I got from the statistical science interview of Myles and Glee, I think at Stanford around 1972. We all have a lot to be embarrassed about for the 70s. So it's not fair to embarrass Myles without embarrassing myself. That's undergraduate days for me. And in the conversation that Myles had with Frank Samaniego, he emphasized how inspiring it was to be at Stanford. And for him, the late 60s, for me, the late 70s. And that's, took me back, and also I could second that with enthusiasm. It was a very exciting time for statistics, almost as exciting as now. And it was a very exciting time to be at Stanford with all the visitors coming through and so on. I remember one of my fellow students saying, the most fun thing to do here is work. And that was absolutely true. We've shadowed each other a little bit. Sam mentioned that he was department chair twice, and I don't know if this picture was taken when Myles was department chair, but it kind of looks like one of those corporate type pictures that they take and put in the dean's office. So I thought it might be. There's my version. I only did one term as chair, nearly killed me, but it was also very interesting. And we've also, this is one of Myles' first publications, maybe his first one in the Annals of Statistics, asymptotically distribution-free multiple comparison procedure. So this is based on Myles' thesis with Lincoln Moses. And a little bit later, I published a paper also on rank statistics in the Annals of Statistics. So we have had a lot of overlap in various ways, both through leadership and research and locations that we visited. So the talk was called 3 R's, and I added reliability and a nod to Myles' work on reliability. And I wanted to talk about that first. But of course, the 2 R's that we've spent a lot of time worrying about recently are replicability and reproducibility, and I'll get to that. But I wanted to start here. And so I started, like we all do when you're not sure what to do, look on Google and see what people are saying about reliability. So this is maybe broader than the work that Myles did. Or what I mean is broader than what we usually think of as reliability in statistics. And so the first few things I found were, in a way, a little bit uninteresting. Reliability is a measure of the stability or consistency of test scores, or the extent to which a scale produces consistent results, or an overall consistency of a measure. Here, we'll also known as reproducibility, so it's starting to get a little bit confused. But if I dug a little deeper beyond the social sciences and medical sciences, where it's consistency between raters or between measurements or between experiments on the physics webpage, I looked at under ecology, and now we're getting more to a kind of systems view of things. The probability that a system will give a consistent level of performance. And in healthcare, this quote from the Institute for Healthcare Improvement, applying principles of reliability to healthcare systems. So that kind of broadens it a little closer to what we're used to in thinking about statistical science. This is a very nice paper by Myles and his student Ed Silpena in statistical science. I wasn't able to get a copy of Myles' Northern Award lecture. I think it has been published, but well, I would have been able to, but I had to pay a lot of money for it, so I didn't. So I read the non-parametric methods in reliability, but just to emphasize that when he turned his thinking to reliability, he emphasized again the sort of non-parametric approach that he developed through his thesis. And the system's view of reliability, of course, is that we have a system of components, and we need to depend on the functioning of all the components, or at least the critical pathway of components. There'll be some redundant ones, of course, and then we need to know the effect of component failures on the system, and that automatically makes it a harder and a more interesting problem. So then I wondered if it was helpful to view statistical science as a system, and if it is, what would its components be? How would we ensure the reliability of the components and of the system? Well, I'm not sure if it is or not, but this is what I'd thought of. You could think of statistical science as a kind of social system. Our students, our professional statisticians, our academic researchers, our collaborators in other disciplines. And we rely on their work to be at the highest standard and also at the highest standards of professional ethics. So the American Statistical Association, of course, has ethical guidelines, and other statistical organizations do as well. So that's maybe one kind of reliability, that people will do the best of their ability. Now it needs to be part of our training, of course, of our students to learn about these things. Another focus might be to think of it as a data system, a collection, the preparation, the analysis, conclusions, communication, dissemination. Data is at the heart of everything we do, of course. And in that case, I think the system becomes reliable through reproducibility, that with the same data and the same analysis, the numerical findings can be reproduced. And I would say we have been a little bit weak as a group, the statistical scientists, in this type of reproducibility. And I think maybe the rise of data science was in some part a reaction to that, techniques and strategies to make this data system much more reliable through reproducibility. And then, since Myles and I both work on a theory of statistics, maybe we can think of it as a scientific system as well. It has foundations and theory and applications. And in that case, we would evaluate its reliability, I think, through its scientific replicability. That is, we can be somewhat consistent in our discoveries of new principles and new ideas in science. Maybe we have a little bit of work to do there too. Most people say that the noun that's used for a group of statisticians is the disagreement. If you find any two statisticians in a room, they'll have three different opinions. But as a whole, I think when we face outwards, we are more or less on the same page. And I think we do feel that our science should be replicable, both at the foundational level and at the level of applications in science and collaborations with others. To get it a little bit more into the weeds, reproducibility and replicability are difficult choices of words, and we don't have a very good track record of choosing words. I challenge you to respond quickly to the difference between specificity and sensitivity, for example. So our terminology is maybe doesn't help us so much, and there's a lot of confusion about these particular two words as well. The ASA on their webpage says the study is reproducible if you can take the original data and the computer code used to analyze the data and reproduce all the numerical findings. Roger Peng uses this definition in an early blog post, and the ASA credits him with this distinction from replicability, which is repeating the entire study independently of the original investigator. without the use of the original data, but generally using the same methods. I think we've sort of converged on an agreement that these are the right phrases to use. The National Academy of Science said much the same thing in its report. Reproducibility means computational reproducibility. Replicability means obtaining consistent results. I looked at various websites, of course, and I looked at the Association for Computing Machinery. And in their version 1.0, which is the first search that came up, they have it exactly switched. They call replicability computational reproducibility, and the other way around. I won't confuse it by reading it out because then we'll really get confused. They've switched it back, so we're all on the same page, and you can get a badge for publishing with the ACM of results replicated. And there's various levels of badges, but the kind of highest one, or the the one that's most broad in scope, is the replicability badge, which means consistent results. However, Wikipedia doesn't help us. They've mixed it all up again by saying the replication crisis, or reproducibility crisis, or failure to replicate, or failure to reproduce. So they've kind of converged on two words for the same thing. I'll stick with the national academies on this and try to emphasize the two different concepts of reproducibility and replicability. And I mentioned data science because I think that the data science approach to reproducibility has been very successful, and statistics needed a bit of shaking up with that. So I'm going to spend a few minutes on the overlaps and intersections and so on between statistical science and data science. And I'm going to start with a quote from Jenny Bryant, who gave and I've spelled her name wrong. I apologize, Jenny. There's no T on the end. Data science. She gave a talk in 2015 at the Fields Institute, which you can view. It's well worth viewing. And one of the things that really stuck with me in her talk was this slide that said, you can't hold the opinion that data science is just statistics if you also hold the opinion that data wrangling is not statistics. And that kind of drove it home to me at that time, that there really is a science behind data science in terms of being very methodical and skillful and creative about how you make a data flow consistent. But the other thing she said that I didn't notice at the time, but I noticed when I listened to the talk again, is it's important that we build a really big tent. And I couldn't agree more. There's data aplenty to go around, and it is important that we have a really big tent. The best resource that I've found for the kind of interface between statistical data science and data science is the Harvard Data Science Review. And coincidentally, Xiaoli Meng, the editor of the Harvard Data Science Review, has an editorial that he published today called Replicability, Reproducibility, and Reliability. But he didn't call it the 3 R's. I think he called it R cubed. But so great minds think alike, and there's no new idea under the sun. They've just published 2 parallel papers, quite interesting, with lots of commentary on the research aspects of data science. So one by Jeanette Wing, a computer scientist, and the second by Xiuming He and Xihong Lin, well-known statistical scientists. And I found these really fascinating, both because I've been thinking for a long time, what is the research part of data science? Is data science a job or a set of courses, or is it a new field of research? So I was really anxious to read this, and there's a lot of great ideas there. I'm going to actually put all 10 challenges out from both sides, but I'm going to do it a little bit slowly because they overlap a lot. And so I'm not putting them in their original order, but I'm trying to group them here in an overlapping, intersecting order. Jeanette had her as her first understanding algorithms. So this, and in the context, I've abbreviated these considerably so they would fit on the slide, but well worth having a look at the full explanation. The idea being that the deep learning algorithms that people are relying on for things are not very explainable. and assuming, and Shihong came up with something quite similar as a challenge of fair and interpretable learning. Both mentioned causal inference or causal reasoning as a challenge area. A multiple heterogeneous data or integrative analysis of data types. And the examples I'm going to talk about have that in spades, so I won't dwell on that, but I think it'll become clear later, at least two versions of that interpretation. Jeanette had precious data, by which she meant data that's somewhat rare. So extreme values, for example, you might have a very large data set, but the values that are really telling you about the phenomenon you're interested in are very few and far between. That was an example of precious data. Assuming, and Shihong mentioned quantitative precision, and I put emerging data challenges with that. I think those are they're really addressing similar concepts. Both mentioned privacy, a key feature. Now, Jeanette's fifth one was inferring from noisy and incomplete data, which I would have thought was squarely in the statistical science side of things. So I thought it was interesting that a computer scientist suggested this. On the other hand, Suming and Shihong mentioned scalable and distributed inference, which I would have thought was squarely on the computer science side of things. And then there are three pretty computer sciencey things in Jeanette's list. Trustworthy AI, although that might have gone with fair and interpretable learning. Computing systems for data intensive applications. Automating front-end strategies. Automating data gathering, I would say, or data querying. And there were some fairly mainstream statistical ideas, as we might expect, in Shuming and Shihong's post-selection inference, a topic of considerable interest now, statistical computational efficiency, and design for reproducibility and replicability, so designing that in. So, but I think what's quite interesting is all the commonalities here and the crossover. It is a big tent if you think about it from a high level sort of point of view. Oh, and I forgot, Jeanette's last one was ethics. And I think, well, in my opinion, we could move that over and have it kind of underline everything we do. Maybe it's not emphasized as much as it used to be, but it's certainly becoming something that we're all more aware of. You may have many others to add to this. I've run out of slide room. I had some thoughts as I went along, but I can highly recommend both papers to challenge your thinking about statistics and data science. I'm going to look at it from a slightly different point of view now. My go-to resource is the book Principles of Applied Statistics by Cox and Donnelly. And they set out a kind of idealized sequence of events when you're looking at a statistical analysis, and starting with a scientific question and thinking about how data could shed light on this, planning the data collection and considering, as you do that, sources of variation and how to minimize their impact. This, I think, statisticians have pretty good training in and are pretty familiar with many of these aspects, even if we might not be at the scientific question stage. We're used to thinking of how to plan data collection. The sort of second part after that, developing strategies for data analysis, modeling, computation, methods of analysis, and assessing the properties of the methods and their impact on the question at hand. Well, this is squarely in our wheelhouse, I would say, and maybe we spend a little bit too much time teaching our students this part and not enough on the first and the next part, but it's certainly very key to statistical science. And then I think as our field has grown in importance and impact, we've realized how important it is to communicate the results, both accurately, but also not pessimistically, not to be always yes, but in the room as we kind of make an impact on the wider scene. For this, visualization strategies are key, of course, as is conveyance of uncertainties and probably the best resource, or one of the best resources, is the work of David Spiegelhalter at the Winton Center for the Public Understanding of Risk. So this is our kind of public-facing view that I think have really, that's been a huge change in the last maybe 10 or 15 years of statistical science, that we're very keenly aware of the importance of this public-facing view. So I have a data science version of this as well, which is taken really, I give a shout out to my colleagues Raymond Ng and Tamer, of course, Tamer Azu at the University of Waterloo, and Raymond's at the University of British Columbia. We worked pretty hard on a network grant proposal for data science and statistical science. And we set out our workflow kind of like this. So we talked about the data acquisition, making the data trustable and usable, the management of the data. We had modeling and analysis kind of crammed into a small part in the middle. And we had a big emphasis on dissemination, visualization, and preservation. And across all of that, we had the security concerns, privacy concerns, ethics, policy, and impact. So this was our kind of, the way we say, I don't know if it was the best way. Well, obviously it wasn't the best way. We didn't get the grant, but it was the best way we could think of at the time. And it spoke to me at the time. I thought it was well put together. So I'm going to put those side by side now. And just to show again the overlap, the scientific planning and the data acquisition. The management of data, I think really, we need computer science to help us with this. Statistical scientists are not well trained in this, but the sources of variation we're pretty familiar with, and we know how to be skeptical about where the data came from. The modeling and analysis is pretty common to both, but the properties of the methods, that's where the theoretical parts come into our discipline. Whereas in computer science, maybe computational efficiency and other aspects of computational feasibility and so on are of more interest. The data analysis and preservation, I think we do really need to be collaborating with computer scientists on this. And then the communication for all of us to do, dissemination, communication, visualization, and so on. So those are, I don't know, kind of the big tent pictures of the interface. And so I want to kind of illustrate how this is playing out, in my opinion, in real time through some examples. These are examples of statistics in the news. This has been a hobby of mine for my career. I love collecting articles from various media sources, and where I see the headline and I think, I bet there's some stats behind that. And then drilling down through and finding what the stats is. If you've heard me give public lectures before, you know that this is the part that I always come alive with, because I just love doing it. It's so much fun. I'm a bit too addicted to it, actually. Well, there's a lot of statistics in the news right now. I gave myself a very hard constraint: no COVID. It's Friday, we should take a day off. So no examples related to COVID, although there are, of course, dozens, very interesting ones, and no election polls. So we'd give ourselves a little weekend break. So my first example, again, thank you, Harvard Data Science Review. There's a really interesting interview with Matthew Selganic in again, the latest issue called Prediction, Machine Learning in Individual Lives. And it's about a study that he and many, many co-authors published in the Proceedings of the National Academy of Sciences, called Measuring the Predictability of Life Outcomes with a Scientific Mass Collaboration. And this was a summary. The PNAS papers are short, so it was a summary, but there's a whole special collection of papers on this, called what he called the Fragile Families Challenge. And as you can see, the paper had many, many, many co-authors. I think maybe as many as 150 co-authors. So this was really interesting. It uses a database called the Fragile Families Database, which started to be established in 2000. in the social sciences. It's a longitudinal survey of about 4,700 births. And there's a extreme oversampling of births to couples who are unmarried. It's a very well carried out survey, stratified random sample of all large US cities, and then a random sample of hospitals within cities, and random samples of married and unmarried births within the hospitals, with, as you can see, oversampling of unmarried births. This is available for use by sociologists and others. And there's a website called Fragile Families where you can find out more about it. Imagine the effort that this took just to even get started, the samples of hospitals, and then getting permission to go and talk to new mothers and fathers in the hospitals at the time of birth, pilot projects and so on. Absolutely amazing. And the data set has been used by sociologists. I think Matthew said there have been about 750 publications to date using this database. 6 waves of data collection at birth, and then at ages 1, 3, 5, 9, and 15. Each wave had a number of modules for data collection. Each module had a number of topics. There were in-home assessments at ages 3, 5, and 9. This is a massive effort. And the idea behind the challenge, the Fragile Families Challenge, was that just around the time of wave 6, where the children were now 15 years old, the data was available, but not to everyone. It was available to the group that were running the Fragile Families collection, but it wasn't available to general social scientists yet. So Matthew and his colleagues had an idea to use the data from the first 5 waves, the background data, to take the data from wave 6 and label it, and then to have a kind of Netflix challenge to predict the outcomes, certain outcomes of interest to social scientists on the remaining data from wave 6. It's best seen in the picture, and a kind of familiar picture from Kaggle type competitions. So you see there's 4,000 and odd families available, and 12,000, almost 13,000 measurements from birth to age 9. And then some training data that was released to the teams from the age 15 wave 6. Some holdout data for a leaderboard so that the groups could submit their algorithms to the leaderboard and see what their results were, and then resubmit and so on. And then finally, when the challenge was over, the winners were picked using the holdout data. So the interview in Harvard Data Science Review is about this kind of machine learning-ish, Kaggle, Netflix type challenge, but with this very interesting and very rich longitudinal survey from the social scientists. The challenge was to predict any or all the teams could choose of 6 outcome variables. 3 were continuous and 3 were binary. And they were also in groups of 2 in the type of interest that they held for social scientists. 2 were about the children, 2 were about the families, and 2 were about, I forget, but it was kind of divided in using the theory of social science and the things people might be interested in. As I mentioned, it was evaluated on leaderboard data, and then the final evaluations on the holdout data. And the teams had to agree to make all their code available so that these can be queried now even after the competition is over. What was interesting in the results section was in the interview with Matthew is even the best predictions were not terribly accurate. And the best submissions were only somewhat better than a simple benchmark that used either linear or logistic regression. This was a benchmark that Matthew and his team put together. So this was, I think, a surprise for everyone. And the teams used a real variety of different data processing and statistical learning techniques. But in spite of the diversity in their techniques, the resulting predictions were quite similar. Now, if you're a statistician watching this, you might think, aha, I knew it. Like machine learning really is, often not as good as good old logistic regression with 4 variables. Fine. But my point is not to show that really, because the best submissions were actually machine learning submissions that used something more complicated than logistic regression. But it's kind of interesting that the data itself is that noisy that it's a little bit hard to distinguish. And the reason seems to be that within each outcome that they were predicting, the squared prediction error was strongly associated with the family and weakly associated with the technique. So maybe predictions at the level of a family are, the data is really not suitable for that purpose, perhaps. I'm not sure. The social scientists will have to tell us really, thinking about this, what some of the issues were. But I found it very interesting. This is a kind of pictorial expression of this, this fact. So the best submissions are in blue, and the benchmark submissions are in green. And this is a measure of the predictability of the outcome, which would be 1 if the predictions were perfect, and 0 if they're useless. And you can see that they're really not getting very close to 1 here. The y-axis only goes up as far as approximately 0.3. The first 3 here, material hardship, GPA, and something called grit, which is carefully explained in the paper, but a measure of resilience, I guess. They're continuous variables, and the 3 to the right are dichotomous variables, and they turned out to be, generally speaking, harder to predict. So some of the conclusions in their National Academies paper, Alexandra Choldachova has a very interesting paper on this, raising the alarm really that policymakers are using black box models to predict outcomes for children that then determine what policy will be set in place. This is kind of a very big red flag, I think, this study for us, that we should be rethinking that. Another conclusion that's in the Selganic paper is that maybe the sociological theory is needed to understand this difficulty of prediction. And he makes an interesting analogy to the weather or the stock market, which is also really hard to predict. Maybe family behavior is just too hard to predict, and that suggests maybe a whole different approach to the sociology of family well-being. And also very interesting for us and our big tent colleagues in data science and computer science, the code and predictions are open source. And maybe this study can serve as a template for similar challenges in social sciences and other sciences. So it's kind of taking that machine learning competition outside of the usual. I thought of many things, and I'm sure you've already thought of others. These are just in reading the article, there seems to be a lot of questions for statistical methodology and theory. There's a lot of missing data in this database, as you might expect, but much of it is missing by design, and some of it is missing for the usual reasons that people just didn't answer the question. The distribution of the responses is quite skewed. There's a slide on the next slide has a picture of this. There's a really interesting discussion by Matthew about bottom-up versus top-down approaches. By and large, the sociologists that competed in a competition started with very simple models and made them more complex. And the machine learning group started with very complex models and tried to make them more simple. And in any case, neither of them did terribly well at predicting, but it's just an interesting kind of sociological approach. Certainly, my approach is much more comfortable with the bottom-up. It's a traditional classical statistical approach. And as I mentioned, the binary variables were much harder to predict than the continuous ones. So I think there's lots of interesting theoretical challenges as well. There's a picture of the skewness of the data. GPA seems to have a bit of a long lower tail. So does grit, material hardship, really quite skewed most families not experiencing material hardship. It's almost maybe a binary variable. And you can find more about this. There's a whole special issue of the journal Socius that summarizes the challenge and the results, and then there's a number of papers explaining the different methods. That's a really great example of a publicly available, very large database, and a very innovative use of the database to tell us not just about sociology, but about statistical science and data science and machine learning and so on. My second example is from the physical sciences. These are a lot harder to read because they have a lot of technical detail, but I started looking into it because there was something in the Toronto paper, the Globe and Mail, called Toronto's National Newspaper in Canada. It's very Toronto-centric, but it's published across the country. Nitrous oxide is a growing threat to climate. And this was actually quite a good scientific article about this study that was published, in this case, in Nature. And that's a picture of the emissions of nitrous oxide around the world. So where did this story come from? Well, probably the journalist got it from Science News. Science News got it from the University of East Anglia. The University of East Anglia has a communications department that will publish results that they think might be of interest from their researchers. And the lead researchers were from the University of East Anglia and also from Auburn University in Georgia. And the Auburn University newsroom also published a news release. I find this happens a lot, that the headlines seem to come from more or less from university news departments, and some are more active than others, of course. And often the article written by the journalist will be pretty close to what the university release was. These will often get picked up around the world, but in this particular case, I found very few news sources that picked up this story, possibly because it's a difficult one, as we'll see in a minute. There's several in Canada, not very many in the US. The Stanford News article was the clearest and the most helpful to me. The New York Times and the Washington Post, for example, did not pick this story up, as far as I can tell. So it's based on a paper in Nature by the lead author is Tian, and there's, again, many, many people. And it's a comprehensive quantification of global nitrous oxide sources and sinks. So nitrous oxide is a greenhouse gas. It doesn't get as much attention as carbon, but it stays longer in the atmosphere, so it's potentially, in a sense, more important, or at least as important. And as you might imagine, a culmination of a long effort, a 5-year effort that brought together experts in ocean, forest, soil, and freshwater systems, among others. And Professor Basu at the University of Waterloo was quoted in the Globe and Mail as saying the biggest surprise is that the rate of increase is higher than other emission scenarios that have been developed by the Intergovernmental Panel on Climate Change. So I guess my flag is like, well, why was this a surprise, and what kind of methods did they use to get there, and are they right, or is the IPCC right? I don't have answers to those questions. The paper was too hard for me. But as an example, it constructed a total of 43 what they call flux estimates, which is estimates of emissions of NO2, 30 using bottom-up approaches and 5 using top-down approaches, and 8 other estimates using observation and modeling approaches. Now, I mentioned bottom-up and top-down in the sociology. This is different. This is really bottom-up from land to sky, and top-down is from sky down to land, or from the upper atmosphere down to the land. And they've synthesized data from a number of sources: terrestrial biosphere models, global ocean biogeochemistry models, dynamic land system, ecosystem models. So these 30 bottom-up approaches basically are built on climate modeling data sets that are available to people who know how to use them. And there's many of them. There's many different versions of climate modeling and comparisons among the models. So they're not just like temperature models, but climate models that use, that provide or build information about the biosphere, models that focus on chemistry of the global ocean, and so on. There's just a mind-boggling number of them available. The estimates of NO2 in the atmosphere are typically from simulations, and then there are some actual measurements. If we had good enough measurements, of course, from all the countries around the world about their NO2 emissions, then maybe this modeling wouldn't be so necessary, but we don't. Although it's part of the Paris Climate Accords, many countries don't have the capacity or the willingness to provide these estimates in a form that scientists can use. So a picture's worth more than my words. This is a figure 1 from the paper, and it illustrates the various bottom-up, the arrows going up, and top-down approaches. Blue and green are kind of natural sources of NO2. It's absorbed by the oceans, also emitted by soils and so on. And then the pink and the red and the orange are anthropogenic sources from humans. And the headline was about the agriculture arrow, the red arrow at the left, the big fat one. So they're estimating that the sources of N2O, I keep saying NO2, the sources of N2O from agriculture are quite large, meaningful in terms of climate warming, and actionable. We could reduce our use of agricultural N2O. You might remember I mentioned that the professor at Waterloo said what was surprising is that they don't agree with the IPCC predictions. And this is a picture to illustrate what's meant by that. Well, 2 pictures, this slide and the next one, to illustrate what's meant by that they don't agree. So the predictions that the researchers made are on the left, the little wiggly lines. There's a blue one and a yellow one, and a black one, which is the average of the blue and the yellow. So the blue are the bottom up, the land emission sources, and the yellow are the top down. And so the average emissions from, you see it goes from 2000 to about 2016, are estimated by that very wiggly line. But the other straighter lines are the predictions of the Intergovernmental Panel on Climate Change. These are called the RCP predictions, and I can never quite remember what RCP stands for, and I've forgotten again because I didn't write it down. But it's a kind of it's a prediction of what might happen under various scenarios. So if we all met our Paris emissions goals, we'd be on the blue line at the bottom where the RCP is low. And if we don't do anything at all, we might be at the red line where the RCP is high. So these are kind of various scenarios. They're projections. The P is for projections, but it's not regional climate projections. It's something harder to remember than that. And the Intergovernmental Panel is changing over to the SSP predictions, which are shared socioeconomic pathways. And the P is for pathways on the RCP as well. So whether you use the new version or the old version, this wiggly line is quite far above what we are hoping for if we get our act together, which is the lowest, of course, of the prediction of the pathways, or at worst, maybe the medium pathway, and these are well above that. This is for emissions, and then the next slide is similar, but for atmospheric concentration. This one is maybe a little bit easier to see, because the atmospheric concentration that's being worked out in this paper is this thick gray line that goes from 2000 to about 2018. And you can see it's just above the RCP 8.5 line, or the SSP 3 to 7 curve, I guess. And that's, so the idea is that once you've accounted for all the sources of N2O emissions and concentrations, it seems that the IPCC assessments are overly optimistic. That these emissions are above what those assessments might suggest. This should worry us all. I don't know if the work is replicable or reproducible. I think it would be quite difficult to reproduce it because it relies on so many different data sources, but I don't know the answer to that. I should maybe pause and ask Elizabeth how much time I have left, because I'm notoriously bad at keeping track of that.
Hi, Nancy. You have about 15 minutes.
Okay, thanks, Elizabeth. Yeah. Okay, so I mentioned statistics and data science and the big tent. This is multi-scale data on a major scale, right? Global climate, biosphere models, the observational databases, atmospheric physics. There's a lot of statistical methods in the paper used for sanity checks. For example, N2O interacts with carbon emission so that there's a kind of feedback loop. And this is illustrated in one of the pictures in their extended data. The sort of extra information at the end of the paper. You see, I've just put in this two little plots of regression because I understood what they were, linear regression plots. So statistical methods are used throughout to double check and build support for various discoveries along the way as they explore these databases. This is showing difference in the impact of temperature on the N2O emissions under a global warming scenario on the right and under a stable 1890 scenario on the left. And you can see that they've checked this with ordinary linear regression, which is kind of a relief. So I think if we think back to these research challenge areas, we've covered a lot of them in this paper alone, and particularly the integrative analysis, the different sources of data and so on. So the last portion of my talk, I want to come back to statistical theory. I've spent my career studying statistical theory. I remember going to see Rupert Miller in his office when I was looking for a supervisor for my PhD work. And he said, well, what do you like? What would you like to work on? And I said, well, I really like math stat, but I think all the interesting problems have been solved. And he kind of smiled and said, well, there might be one or two others that haven't yet been solved. And that was extremely good advice for me. So I'm forever grateful to him and the theoretical atmosphere at Stanford that welcomed this. At the same time that people were very much engaged with applications. Well, Myles, I think, was tarred with the same brush. Lincoln was both theoretical and very scientific. So I wanted to talk a little bit about that some more. The non-parametric methods book that I have on my shelf and have used very often that Myles wrote with Doug Wolf, and the third edition was published in 2015. It's maybe not what you think of nowadays if you scan through our theoretical journals and look for non-parametrics. There you might see things like concentration inequalities and contraction rates and infinite dimensional Bernstein-von Mises theorems. And it's really kind of gone very theoretical because the mathematical analysis is both difficult and interesting. Now, Myles does have work on non-parametric Bayes and in particular Dirichlet process priors in the book, but there's many more now that are seem to me to be more complicated and a little bit harder to understand. And it kind of feels like the rank tests that Myles and I worked on back in the day are kind of gone the way of the Pearson classification of distributions or something. But I've learned over a long career what goes around comes around. And the latest issue of the Scandinavian Journal of Statistics, to my surprise, has a paper on the log rank test for the two-sample problem. So there you go. Ranks are back in reproducing kernel Hilbert spaces. I also wanted to mention that this sequence model that appears in a lot of the work in high dimensional regression as a simple example of a high dimensional problem, because n is going to infinity and there's one parameter for every observation. So it's not exactly non-parametric because we're assuming that y follows a normal distribution, but because the thetas are so crazily unconstrained, it's almost like a non-parametric problem. Of course, we can't make any progress without assuming that the thetas are sparse or something like that. But it is a kind of an interesting bridge between parametric and non-parametric inference, and relates back to Stein's work in the early mid-50s and early 60s. Non-parametrics played a role in this Nature paper as well. And this was a bit of a surprise for me. So these are all the pages of the paper that you can't read them. You're not meant to. There's the page 250 is where I took that picture from. And like most Nature papers, they're very short. It's about 7 pages long. And so page 255 is all the list of references and so on. But the one that I like to zoom in on is the one that's circled in blue. And that's where the methods are. They're always at the end after all the references. I guess they figure nobody's going to read it, but I like to look at them. And these methods are, all the papers have this no matter what field they're from. Typically, they'll have a set of terminology, background, data sources, if it's an experiment, the experimental methods and so on, and the statistical methods. So I kind of flip through this methods section till I get to the statistical methods. To my surprise, the statistical methods for this paper was the shortest one I've ever seen. It's 1 sentence. And the sentence is, the Mann-Kendall test was used to assess the significance of trends in annual N2O emissions. The Mann-Kendall test is a rank-based test for trend, just like the Mann-Whitney test, but it's for trend instead of for difference in 2 groups. So there's another rank test, Myles, for us, used in some of the latest work. They sold their statistics short. I'm a little bit surprised Nature let them get away with this because, as you could imagine, the whole paper is crammed with statistical methods. So what is the role of theory in all of this? I mean, these data examples are fascinating. And if you start to work on one, it will take you months or years to get through it. And it would be hard to keep theoretical statistics top of mind. But the role of theory, I think, is to think about generalizable strategies and principles that we use to develop these. And this was a point that David Cox and I made in a paper that was published in the International Statistical Review in 2013. So I put this slide in many talks because it helps me to remember how important theory is and why it's important. How do we evaluate these strategies? And we have a very long history of this. I think that's a kind of unique contribution that we can make to the big tent of statistical science, data science, and science. And one of the, of course, we've developed various techniques, including our favorite confidence intervals and p-values and estimates and standard errors. P-values are in a bit of trouble, as we know. David Spiegelhalter had this tweet about a year ago. This paper motivates the call for the end of significance. That he found it appalling that because the p was slightly bigger than 0.05, the researchers concluded there was no reduction in mortality. He said that's why we call for not to use p-values anymore. What he really means is don't use p equals 0.05 as a threshold. And this comment in Nature from about 4 years ago retires statistical significance. The ASA has made a public statement on statistical significance and p-values. Again, Harvard Data Science Review, p-values on trial, a very interesting article by Deborah Mayo about the use of p-values in the court system. So they are causing us a certain amount of trouble related to reproducibility and replicability. But I don't think they're really the problem. The problem is that people want to look for fast and easy answers, and p less than 0.05 sounds like a fast and easy answer. But we have to keep reminding people that science is a process. Learning is incremental. Probability expresses uncertainty. It could be epistemic uncertainty. I just don't know. I am uncertain, or we are uncertain about this. Or it could be empirical uncertainty. That is, this result will happen in fewer than 3 out of 100 times if this experiment is repeated indefinitely, and so on. So we have either interpretation, but the p-values must be seen in the light of these rather broader points, I think. For scientific advances, I think empirical behavior of our procedures is key. It's not enough to convince ourselves and our close colleagues. We need to show that our work is reproducible and replicable. For decision-making, personal probabilities may have a very important role. Maybe not personal exactly, but we're faced with so many, well, our decision makers are faced now with so many decisions, and they somehow they're relying on data and in probably some personal or local society probabilities that aren't very well formulated. And these are important, but they need to be more properly introduced into the decisions, I think, in order to be effective. A shout out to a paper I'm proud of. Robert Cass took the lead on this, but I worked with a great group of people in putting together for a journal that few of us read, PLOS Computational Biology, 10 Simple Rules for Effective Statistical Practice, in which we did try to drive home this point that the science is a process and statistics can help you along the way, but p less than 0.05 is probably not the answer we should be looking for. That concludes the formal part of my talk. I want to give a very warm thank you to Myles, not only for endowing this lecture for Florida State, which will, of course, be valued in many years to come, but for choosing me to be the inaugural lecturer. I've known Myles for many, many years, and it's a privilege and an honor to give the lecture. Early this week, a very, very heavy box arrived by FedEx to our front door with a very, very heavy vase in it. Thank you so much to Florida State whole team, the department and the dean and all the supporters of this lecture. So I will certainly cherish this lovely reminder. And then I asked our daughter, who's a bit of an artist in her spare time, if she could actually figure out a way for Myles to give me the vase. And she said, she sent me this. So I would be delighted to visit Florida State, and I look forward to a time when I can. And in the meantime, a very warm thank you to you, Myles, and thank you to your audience for listening.
Thank you, Nancy. I'm just delighted that you gave this talk, and it was an excellent talk.
Thanks, Myles.
Let me second that. Thank you very much, Nancy. We really look forward to the time when we can have you here personally and let you tour the campus and see how pretty it is. Now I want to turn this over to my colleague, Dr. Chong Wu. He's going to lead us through questions that come in the Zoom chat window. So please enter your questions there. Chong?
Okay, thank you. Thank you, Elizabeth. So, and there's already have some discussions in the chat box. And those discussions are many regarding the deep learning themes. So the audience want to know what are you thinking for the deep learning especially regarding how to interpret the deep learning, because most of them think they are the black box. We don't have much interpretability for those something called a fancy method.
I agree, and I'm not at all an expert on this. So I'm speaking at a sort of very general level. I I do know that there are colleagues in machine learning and data science who are working on interpretability of deep learning methods, but the deep learning methods that are being marketed by the companies and so on, I think are really not at that level of sophistication yet. This is a research field. So I think it's important that we continue, as many of us who can, to raise the alarm that these methods are not well understood, and while they're not well understood, they can have unforeseen consequences, and we're getting now an arsenal of examples like this. This is an uphill battle, but there are many people working on it, people working on fairness and accountability in AI, which was one of the challenge areas, and people working on ways to get beyond this kind of black box notion. So I think the problem is reasonably widely appreciated among academic researchers. I'm not sure that the problem is appreciated in the more public uses of this, or the more commercial, I should say, uses. And I think that's something that we have to be always raising the alarm about.
Okay, yeah, so another question is regarding the first example for the fragile family challenges. So some audience are very curious why the model selected by the experts just using the 4 variables perform, I think performed similarly to the best model provided by the participants. So they think this is more like if we think about that, the linear regression is just the first thing we learned in statistics. So the machine learning is something more advanced. So they just curious why this is the case for the fragile family studies challenges.
Yes, and I don't think we know why it is the case. Is that much of the interview with the lead author, he expressed his surprise that this was the case, and pondered reasons for this. I guess there's a lot of noise in the data. Individual families, they're asking to predict an event for family by family. There's on the order of 4,000 families in the database. The training set was not terribly large because it used wave 6 mainly, and that was the only labeled data was in wave 6. Oh. There was some background data from waves 1 to 5. I think we just don't know the answer to that, but clearly the data is very noisy, and when the data is really noisy, simple methods can work as well as complex methods. I think is like, I'm sure I've said that many times, and most statisticians of a certain age will always be, if you bring them an applied data problem, they'll say, keep it simple, make it simpler, make it simpler. But right now, that's not quite the fashion. And so this, I don't know. We'd all like to know why that's the case, I think.
Yeah, so another question is regarding the reproducibility. So I'm collaborating with epidemiologists. So in their field, they really emphasize the reproducibility. So when they conduct the analysis, they will have an independent data set to test. But in our thinking, we think there's not much difference if we do cross validations or we use an independent data set to test. The results will be quite similar in terms of the say which method performs better. But they think totally differently. I'm just curious, what's your opinions regarding that? So.
Well, again, I'm not an expert at all in that type of analysis. My sense is that cross-validation can sometimes be a bit misleading, and an independent data set is really a more closer to what we think of as scientific replicability. And we may not have such an independent data set, so we may need to use for cross-validation. But I think if I were advising someone, and I normally wouldn't be because my applied chops are not as good as my theory chops, but I would be a little bit reluctant to rely on cross-validation unless it was necessary. I don't know what the state of the art is in that debate, but if it's not settled, then there's very interesting theoretical problems to be looked at for sure.
Okay, so yeah, there's many questions from the, let me think. If you have questions, please please type in the chat box, because there are so many people say this is an excellent talk, and thank you to give us this talk. So there are so many messages in the chat box. It's really hard to find the questions.
But you know what? It's very rewarding to see all those thank yous in the chat box. It's a very nice feeling for a Friday afternoon. So thanks, everybody.
So there's a question. What, in your view, is the most interesting and important open problem today in the mathematical theory of statistics? So regarding the theory part.
Oh my goodness, the most interesting open problem in the theory of statistics. Oh boy. That's a very hard question to answer, but I think there's a lot of very, very interesting work going on right now in the asymptotic theory when P increases with N in various forms. So I say that because I'd spent a lot of time working on asymptotic theory, so it interests me still. And there's some fascinating work when P over N goes to a constant. We're getting new distributions for likelihood type quantities from Immanuel Candace and his students, Pragyasur and so on, building on work of Donahoe and Johnston. And so I find that quite fascinating and not well understood. But someone else will have their own favorite in non-parametric Bayes, or Myles might have his own favorite on the modern use of rank statistics or the modern use of reliability. There's lots. It's a big tent. There's many, many interesting things to work on.
Yeah. So, yeah, I think yes, I agree. I think for the asymptotic, for the high dimensional problems, even though we are in the big data field, but I'm working on the stat genetics. I still think those methods are super useful. Even right now, the N is around 500,000 to 1 million, but for some specific problem, it's still N smaller than P. Yeah, so I totally agree with those parts. But there's another question regarding the p-values. There are lots of people ask you, do you think the p-value is dead, or what's the place of the p-value?
I think p-values are perfectly useful things that can help you a lot, but they're just not a decision-making tool. And they shouldn't be a decision-making tool for whether you keep going or give up, or whether you publish or don't publish, and so on. There's no magic value of P that makes the results interesting, and beyond that, they're not interesting. But it's perfectly sensible probability, the probability that you would observe this result if there was nothing going on is perfectly interpretable in the context of most applications. It's not the p-value that's the problem. It's the use of the urge to look for quick solutions is the problem, not the p-value.
Okay. So that means it's just because people do not use that carefully enough.
Yes.
They just use the magic cutoff point.
Absolutely. Yes, absolutely.
Another question is, do the Bayesian posterior distribution provide a better basis than the p-value for decision making?
Well, yes and no. Yes, if you have a prior that's justifiable. Yes, if you're sure your MC-MC algorithm has converged, which we're not always sure, right? Yes, if you're sure that your posterior gives replicable scientific results. So that meaning if you're going to use this particular procedure, it should be repeatable in repeated instances of data from the same model. And if it's not, then you have a problem. And it's hard to assess all those things from a Bayesian posterior, especially if you build it up, as people often do, hierarchically with a few flat priors here and a few vague priors there, it's hard to know if what you've got out at the end has the properties that it would be repeatable with new data from the same model, for example. So I think in principle, it can be an improvement, but in practice, it needs careful thought whether in this particular instance, it's going to be an improvement or not. There's no blanket answer to that, I don't think.
Okay, so that's the next question. There has been a push to provide more documentation, data, etc. while submitting papers. Do you think there should be a stronger push for this across publications? And what do you think is the bare minimum that authors should provide to the journals to support their publication? I guess it's regarding the producibility.
Yes, well, again, it's hard to answer that question in the abstract. There is, I think, a very welcome push to insist that when authors submit a paper and they say code is available from the authors, that's no longer good enough. I've been guilty of the same. The code is available as long as the PhD student is still a PhD student, and after that, it's gone. So I think that it's a very welcome push to be more responsible in that, to have code that can be reused and code that you can share with others. Making the data available it's very difficult at different levels of research, right? Like it's sometimes extremely expensive and difficult for a researcher to provide the data. In some fields, in other fields, it would be easy. Just put the database in the back of the paper with code. So I don't think there's an easy answer all around, but I do know that people who are working with big data sets and are asked to make this data available, they do note that it's very expensive and time consuming to make the data really clean and available to everyone for reuse. And so if we value that, we're going to need to pay for it. But I couldn't pick a cutoff that, this will be enough and that won't be enough. It'll depend on the application, it'll depend on the field, and it'll depend on the ability of the researchers to do that.
Yeah, thank you. Thank you, Nancy. So let me turn off my microphone to Elizabeth for final remark.
Thank you very much. Again, I just want to thank Nancy for being our inaugural Hollander lecturer. It's been a fabulous morning. We're into the afternoon now. Nancy, just so much. Thank you. Thank you.
Thank you, Elizabeth. Thanks for the invitation. It was a pleasure. I enjoyed putting it together, and it's a pleasure to imagine that I might be at Florida State in nice warm weather. It's very cold here today in Toronto.